In this video, I wanted to talk about taking derivatives of a product of two different functions. In the last video series, we talked about rules for differentiation, such as the power rule, the constant rule, the coefficient rule, and the sum and difference rule. Let's quickly warm up with a review of those rules because we'll be using them again as we work with the product rule. All of these rules build on each other, and we need to remember our previous rules as we progress. So say we have a polynomial function. We can always solve the derivative of it, which we sometimes write as f prime or y prime or dy dx, by dropping the power and subtracting 1. So we'd have 5x to the fourth. So we bring the power in front as a multiplier, subtract 1 from the exponent, and there we have our derivative, which again, in previous videos we talked about why that's the case, as well as how do we use that rule. Now, another rule to remember is that if we have a constant function, the derivative is always 0, which you can always think of as an x to the 0 power. If we have a coefficient in front of our function, polynomial, whatever the function is actually, doesn't matter, this will not affect the derivative. So if we're taking the derivative with respect to x, we can just ignore the multiplier for the purposes of the derivative, take the derivative of x cubed by dropping the 3, subtracting 1, and 3 will just multiply into the 7. So we'll have dy dx equal to 7 times 3 is 21, x squared as our derivative of 7x cubed. And the last rule that we covered in the previous video series was the sum and difference rule, which says that if we have a sum or a difference of two functions, we take the derivatives individually. So I take the derivative of this minus the derivative of this. So if I wanted to know what's the derivative of this two-termed polynomial, we drop the 4 and subtract 1, leave the minus alone, and then just take the derivative again of this x squared on its own. So drop the 2, 2 times 11 is 22, and 2 minus 1 would leave us with a single x. And that's a review of our rules leading up into the product rule. So the primary goal of this video was to discuss, well, what happens if we have, instead of adding or subtracting, as we covered in the last couple videos, what happens if they are instead multiplied? And before we do anything, I like to say that multiplying is not as straightforward. You cannot just take derivatives of individual components of the function. Sadly, it does not work that way. It's a little bit more difficult. It's sort of like if you're multiplying out polynomials. Like let's look at an example. Say you have x plus 3 times x plus 4. You can't just multiply the first stuff together and then multiply the second stuff together. That is not equal to the full product of those polynomials. And when it comes to, say, we had a product within a derivative, like looking at some examples, like say we wanted to know what is the derivative of this times this, you cannot just take the derivative of this, multiply by the derivative of this. That does not work. And so the product rule, let's go ahead and look at it as it appears in our book, because there's a few shorter ways of writing it that I more prevalently would write it, or there's also a mnemonic, how I like to say it, which is the derivative of f times g. So again, a product of two functions is equal to f times the derivative of g plus g times the derivative of f. Or what this is saying is I need to take the first function, multiply that by the derivative of the second function, and add that to the second function times the derivative of the first. Or the mnemonic that my teacher taught me when I was in high school that I still remember, so definitely an effective mnemonic, is to say first d second plus second d first, where the d represents derivative. And it's sort of, I kind of think of it like foiling, because when I'm foiling polynomials, I end up with four things, right? I have to do this times this, plus this times this, plus this times this, plus this times this. When I am using the product rule, it's actually not four products, but it's four things, so that's where the similarity ends. But yeah, we're just taking first d second plus second d first, and that gives us our full derivative. Now, if you're wondering, well, why does this rule work? This is something where we're not going to get into the nitty-gritty of the algebra, but it turns out that if you apply the difference quotient, because as we know, the definition of a derivative is always the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now, if you use a compound function f and g in there, what you can do is there's some algebra. If you simplify the algebra, this is the end result. Essentially, this is the simplification of what a derivative is, which the book, I believe, will sketch out that proof. So I always recommend to my students that you read the book, look it over for yourself, and don't just take my word for it. But the conclusion is there's this simplification to how a derivative works. And no other, you can't take any other shortcut. You have to use this rule. If you try to do something else, it's not going to work well. Anyways, so another way this is written is, notice if we're using the function notation, because up here we have Leibniz notation with ddx, Leibniz on top of function notation. But if we're just using the shorthand f dot g, meaning multiply f times g, prime in parentheses, meaning if we're taking the derivative of the product of f and g, that's the first times the derivative of the second plus second d first. So again, just this is a shorter way of writing it, which if you're trying to write notes or remember these things is a little bit easier. Or again, using purely prime notation instead of using Leibniz differential operator, we could just write this as if capital F is the product of lowercase f and g, capital F prime, the derivative of that product will be, well, it's actually written backwards here, second d first plus first d second. And it doesn't matter which, addition is commutative, so we could reverse the order. I don't know why I wrote it backwards here, but you might see these other forms in other textbooks, or if you just Google product rule, it should show up, and so on. And one question before we get started is, when do I need to use the product rule? But if you look at a lot of these examples, it's when you have multiplication of two functions involving x. So if you're multiplying stuff which both includes, and sorry, that's not a very technical definition, but this is how I like to think about it. Like if we're looking at this first example, notice we have a two-term polynomial times another two-term polynomial. So those two products both involve x. So, well, sometimes there may be a different way of doing it, like you might be thinking I could just multiply that, as you could. But like looking at another example, again, notice I have this times this. In the third example, 3x squared times e to the x, again, these both involve x. The product rule must be used in those cases. Now, 3, the coefficient, does not need to be involved in the product rule because the 3 can be passed through the differential operator by the coefficient rule. However, that's just how I like to think about it, because in my experience, students often forget about this rule and they'll try to take derivatives individually. So let's work on a few examples and then wrap up this video. So if we look at the first one, notice again I have 4x times 5x to the 9th minus 10x squared. And also, first note is you could just use a distributive property and differentiate this normally by the power rule. However, let's just go ahead and use the product rule as practice. So in this case, we have a first and our second. So what I'll do is I'll label this as our first. Let me highlight things. So we have yellow, I'll call the first, and then I'll call the second in green. And so if we're taking our derivative should be equal to first, copy it exactly as it is, so yellow, and then it's multiplied by d second. So d second would be using the power rule and coefficient rule and so on, every rule that we reviewed at the beginning. I would drop the 9. 9 times 5 is 45, and subtract 1 from the exponent. And then with 10x squared, drop the 2's 20, subtract 1, and it would leave me with 20x. So this would be the first part of my derivative, which would be first d second. So that right there is d second, and this right there is first. And then there's always a secondary term in the product rule. It's first d second plus second d first. So second is just, again, we're going to copy the second exactly as it is, because that's just the second function on its own, and then multiply by the derivative of the first. Now first, for x, another thing that's helpful to remember is the derivative of x is just 1. So 4 times 1 is just going to be 4 for the derivative of the first. So this would be d first. This would be second. So this is going to give me first d second plus second d first. And if we multiply this all out, technically this is the derivative, but we could obviously simplify these polynomials if we multiply and add. So let's go ahead and do that. 4 times 45 is 180. x times x to the 8th is x to the 9th. And then 4 times 20 is 880. So we'd have negative 80x squared. So those would give us our first two terms. And then this 4 again will distribute. So 4 times 5 is 20. And 4 times 10 is 40. And we do have some like terms here. So let's go ahead and clean that up to get our final answer. So if we combine like terms, that's going to give us, well, 180 plus 20 is 200. X to the 9th. And 80 minus 40, negative 80 minus 40 is negative 120, x squared. And this is our derivative. And before we move on, because that's our first example of using the product rule, and really that's all there is to it. If you have a product, use firsty second plus secondy first. But the other thing, as I mentioned at the start of the video, is there's a different way I could have done this, which is just by multiplying first. So let's copy down our problem once again. And you know, multiplying first is usually a lot easier. And so I've been asked the question before, well, why do I bother with the product rule if it's easier to do it another way? And I'll get to that in a second. So my point was we could first have used the distributive property to simplify the inside of our derivative before we actually take the derivative. So 4x times 5x to the 9th would be 20x to the 10. And 4x times 10x squared would be negative 40x cubed, right? So we could simplify our polynomials inside, then use the power rule, right? Because what ddx means is take the derivative of whatever's inside. But whatever's inside, I could use an equivalent representation, right? I could just algebra simplify this first, that makes sense, and then solve the derivative after. So as I'm taking the derivative, right, I no longer, once I evaluate the derivative, I remove my derivative symbol. And so the derivative of the first term, again, I could just use the power rule. So dropping the 10 would give me 200x to the 9. And dropping the 3 times 40 would be 120x squared. And this would give me my derivative using a different technique of solving. And notice it's the same answer. That's what I wanted to illustrate. So as opposed to going into the formal proof of the product rule, I just wanted to demonstrate to you that yes, this rule works. And now to answer the question, why do I need to bother doing this? Because if you look above, this was a lot more work than just multiplying it out. Well, the main reason is that in a lot of situations, you don't have that option. Like looking at functions involving exponentials or sine, a lot of mathematical functions are what are called non-algebraic functions, such as sine, which is called a trigonometric function. If we try to multiply sine x with x squared, you can't simplify that. And so there is no way to do what we did in this case. With polynomials or power functions, you can always use algebra to combine them. So the product rule is not always necessary for polynomials specifically, but with other functions it is, and it's worth learning now because we're going to get to other types of functions. In our course, which is business calculus, we won't get into certain types of functions like trigonometry and so on. But in a general calc course, you would cover the full gambit of all functions, including sine and well, we're going to get into the logarithms in this course too, but anyways, let's do another example. So, and also, I didn't work through the warm-up, but just as another thing to recollect from previous lectures is that if we have a division by x, we can write this using a power function, or if we have radicals, we can change the form. So to start off with this question, again, if we want to know, well, what's the derivative of x, the root square root of x, we could again change the form, and similarly 1 over x, to rewrite these as power functions. Unless you remember, the derivative of 1 over x is negative 1 over x squared, and the derivative of the square root of x is 1 over 2 root x. These are derivatives we've solved in past lectures when we used the definition of the derivative by difference quotient. So these are ones we've solved already, but they're much simpler to just use the power rule. So before I take the derivative, I'm going to leave my ddx in my expression as I simplify it. 1 over x, we could write that as x to the minus 1, because a negative exponent is the same as division. And then the square root of x is the same as a 1/2 power. So in 14, well, that's about as simple as I can go. But my point is these sorts of division and roots of all indices, whether it's a square or a cube or a fourth root or whatever, can always be translated to either a negative exponent or a fractional exponent. And again, my point is now if I'm trying to solve these derivatives, I can just use the power rule. And so now we've simplified our interior a little bit, or technically we haven't simplified it, we've just changed how we wrote it. But now I can use the power rule to progress. Technically, you could use the distributive property to simplify this first if you wanted to, but again, let's just practice with the product rule. I'll leave that as an exercise for you to try on your own to make sure it adds up. But yeah, so let's do it again. Okay, so been rambling for a minute now, but again, it's always going to be first d second plus second d first. So let's highlight first in green and second in yellow. I reversed my colors. Let's be consistent with the. So first will be in yellow and second will be in green. So I'm going to need to do first d second plus second d first. So let's just go ahead and count. Sorry, I realized my audio just cut out. I have no idea how long it is cut out for. I apologize. I have ordered a new mic and it is coming by 10 p.m. today. So hopefully not much was missed. And since I don't know where it cut out, I'm just going to continue. But what I was saying is we always do first d second plus second d first when we have polynomial-like expressions. The we always multiply the coefficients 1 times 1/2, and then we multiply the x's, x times x. And when we multiply power functions, the exponents add together. So -1 plus -1/2 is -3/2. And then moving on to the second term, the -1x to the -2 will distribute. So I'm going to have -1 times 1 is -1. And then I have 1/2 plus -2, which is also -3/2. And then I'll also have 14 times -1x to the -2. So that would be -14, 14 times -1, and then x is not changing because it was all by itself. But I'm just distributing, because in the second part of second d first, we still have to use our normal algebra rules like the distributive property, but the d first will distribute into the second. And so now, again, we can clean this up a little bit because notice we have a like term between the x to the -3/2. So we're going to have a 1/2 minus a 1. 1/2 minus 1 is -1/2 x to the -3/2. And then the x to the -2 is not alike with the others, so we can't add them together when they're different powers. Only when they're the same power can we simplify. And also, so this would be a totally fine answer, which I would accept on any test. and I probably wouldn't give you quite this annoying of an example. Well, maybe not significantly harder than this though. Your homework may have a few that are a little, equally as irritating. Um, However, when it comes to representing the final answer, sometimes certain people might say, we should not represent this using negative or fraction exponents. And since the original expression that we were given was in the form of reciprocals and roots, we can always convert these back to reciprocals and roots, which is fine. In general, I'm not going to make you do this because once you have your answer, you always need to simplify your answer, but whether you write it in one form or another, I don't care, and neither would most people. But anyways, negative exponent will go back to the denominator. So this would give me negative 1 over 2 x to the 3 halves. And 3 halves power is the same as the square root of x cubed. So I have the square root of x cubed for this first term. And the second term is just minus 14. And then x to the minus 2 is also being divided because it's a negative. So I could always change a negative exponent into a positive by flipping it. And a reminder is that only what the exponent is attached to flips. The 14 does not flip. This is a common mistake that I've seen students make. But this would be an alternate form that is, probably the better answer just because it's mimicking the form of the original derivative problem. But anyways, this video is getting long enough, and let's in the next video we'll talk about the product rule.